All right, last couple. We're almost done. Working backwards. What is the energy in electron volts for 434 nanometer blue emission line? How do I know it's an emission? Mostly black and only colors are visible. So it's an emission spectrum. Did you really try it? Here we go. We're talking about energy and we're talking about light, so my brain instantly goes to E equals HF. It's either this one or that other version where we substitute in and we get this. We're given a wavelength. It's blue. Blue is the color. 434 nanometers is the wavelength. Okay, so we have wavelength. And it's a blue line, so it's light. So we also have C. So we have lambda and we have C. All signs are pointing to this equation, but solving for E. So let's go ahead and do that. First, let's fix this thing over here. Just copied and pasted. Sorry. Electron volt times. All right. Let's do it. E equals HC over lambda. Easy, right? Can't be this easy. Pretty easy stuff, mathematically speaking. Conceptually, you really have to think, ask some good questions, have good conversations. Divided by 434 nanometers, so 434 times 10 to the negative 9. Solving all of that, and we get 2.86 electron volts. Made a mistake in the last video. Sorry about that. I looked at my wrong problems. Whoops. Let's do it again. Draw in the energy transition for a 434 nanometer blue emission line. This is a really good question. Something that is absolutely useful for you. You need to know how to do this. Let's hop to it. We know the E equals 202.86 electron volts, right? And remember, this E is not E. It's really that change in E. So all we have to do, where are we seeing a change in energy of 2.86 electron volts? You're just going to subtract these. Looks like we're probably going to end up on N2, right? And then that would be a good starting place. And then I would just say, okay, 3.4 minus 2.86, and I got to 0.54. That's it. That's it. Knowing how to do that is going to help you and ensure that you're passing this exam. Doppler effect. This is a little added bonus here. When we get into astrophysics, then that's when this really starts to come into play again. But remember the Doppler effect when we did sound. There's a little refresher. If you're wearing headphones, you may want to turn down the volume. 3, 2. Close your eyes. And then open them when you realize when this car has passed you. You can hear it, right? Easy. So that same effect where there's an apparent shift in frequency to the observer of sound coming towards them. As the object is moving closer to the person, you're getting a higher frequency. Then when it passes, then you have this apparent lower frequency. Those wavelengths become stretched out. Same thing happens for light. Instead we have blue shifted. So as things are moving towards us, they become shifted to a higher frequency. So they become blue shifted because blue is going to be a higher frequency. And if they're moving away from us, then it's red shifted, red frequency, longer wavelengths. This is an example of how we know the universe is expanding. When we look at all of these galaxies, all of the galaxies are red shifted. So we know they're moving away from us. So they're going outwards. Red shift, blue shift. So the Doppler shift, if we took our stationary and we red shifted it, everything is just shifted to the red. Just a little bit to the red. And if we took it as if it were stationary and then we shifted it to the blue, then we would say that's moving towards us. Because it's blue shifted, we're getting an apparent higher frequency.